The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Okay. All right, so last time we were talking about the general interactions that are present in a chemical bond. The nuclear-nuclear repulsion, the electron-nuclear attractions, the electron-electron repulsions. And we talked about how the competition of those three interactions are what gave rise to this interaction potential that we drew. It is the competition between those interactions that determines what the bond length of a molecule is. It is the competition between those interactions that determines what the well depth is or the bond strength is in a chemical bond. Well, today what we're going to do is we're going to move on and talk about a specific model for chemical bonding. And the model we're going to talk about is that of Lewis diagrams. Now, interestingly, this is a model that is non-quantum mechanical. This was invented 20 years before quantum mechanics by G.N. Lewis. Somehow G.N. Lewis recognized, and I don't know how he recognized, that's genius, I guess, but he recognized that the key to chemical bonding was a sharing or an overlap of two electrons, one from each atom. And he represented these ideas using these Lewis diagrams in which he took the valence electrons, the total number of valence electrons in the two atoms that were forming a bond, and he redistributed them so that one atom from each, or one electron from each atom that was making this bond shared an electron, and the rest of the valence electrons were distributed amongst those two atoms such that each atom had an octet of electrons around them. Each atom had a rare gas electron configuration. And that's the basis of this idea of Lewis diagrams. The idea of the octet rule. On top of it, there's no chalk today. There's no, I got a piece, okay. The octet rule. Okay, so for example, if you have a fluorine atom with its 7 valence electrons here coming together with another fluorine atom with its 7 valence electrons to make a fluorine molecule. Well, the idea is that each one of these extra electrons now on the fluorine, or these unpaired electrons, are shared between the two fluorines. The result is now, given the sharing, that this fluorine has an octet of electrons around it, right? And this fluorine now has an octet of electrons around it. They have this octet configuration, which is the lower energy filled shell configuration. Now, that's the case, of course, for all the elements except hydrogen. In the case of hydrogen, we're coming in with one atom. Say it's combining or reacting with a chlorine atom. Well, in this case, this electron from the hydrogen is going to be shared with this electron from the chlorine. And now again, this chlorine has this octet around it. But the hydrogen, of course, has just 2 electrons around it. That hydrogen, its inert gas configuration is that of helium, right? And so it is satisfied with just 2 electrons around it. So with this sharing idea, Lewis could really understand the stoichiometry of many compounds. He understood why hydrogen gas was H2 and not a hydrogen atom. He understood why nitrogen gas was N2 and not a nitrogen atom. He could understand why oxygen was O2 and not an oxygen atom. Now, these Lewis diagrams have absolutely nothing to do with orbitals or wave functions, right? which we actually know to be a more accurate description of chemical bonding. And we're going to get to them. But Lewis diagrams work 90% of the time. 90% of the time to tell you where the electrons are in a molecule. It works so well, and it's easy, that chemists have used these Lewis diagrams before quantum mechanics and have continued to use them after quantum mechanics, right? They use them because it's easy and it works. It allows you to understand where the electrons are in a chemical bond, on which atoms the electrons are centered, where the lone pairs are, where those electrons that are in the molecule that actually don't participate in the chemical bond. For example, here in HCl, these two electrons, these two electrons, these two electrons, they aren't participating in the chemical bond. We call these electrons here lone pairs, right? That's an important definition that we're going to use. All right, so we're going to look at this system. Again, it's easy. The alternative is solving the Schrodinger equation, which you don't want to do if you don't have to do, right? Because that's hard. You can't do that quickly. So that's the value here. It's going to give us a framework, these Lewis diagrams, to kind of organize a lot of chemical reactions, to kind of organize our ideas of bonding and what will react with what. All right? Okay, so let's start doing this. And to do that, we're going to have a set of rules here. And let me put this front screen down. And I think, actually on the side screen, could you put my rules up there? Yeah, on the side screen. All right, so the basic idea in Lewis structures is that we're going to take the total number of valence electrons, the total number of electrons, valence electrons in the two atoms that are going to form this bond. We're going to share electrons between the two atoms and then take the rest of the valence electrons and distribute them amongst the two atoms in that molecule such that each atom has an octet configuration. So to draw a Lewis diagram, you're going to have to know what the valence electrons are. In particular, how many valence electrons each atom has. This you have to know really off the top of your head. And this is just a quick list of the number of valence electrons. Carbon has 4, nitrogen has 5, oxygen has 6, et cetera, et cetera. All right, so let's, as an example, illustrate how to draw these Lewis diagrams. Here are our set of rules. We're going to go through them step by step. As you get better at this, you won't have to go through these rules in such detail. But for now, when we're just learning how to do it, I think this is a very effective way. So let's start. Take an easy one. So we want to draw the Lewis structure of methane. First thing you have to do is you have to figure out what the skeletal structure is. You have to kind of figure out as a first pass what's bonded to what. And now I'm going to give you some hints. First of all, hydrogen. If you have a hydrogen atom, that's always what we call a terminal atom. Terminal means that it's only bonded to one other atom. Fluorine atoms also are usually only terminal atoms. All right? Hydrogen always is. Fluorine is 99% of the time only a terminal atom. All right, so in the case of methane, which you know has 4 hydrogens and 1 carbon, if the hydrogens have to be terminal, well then there's only one choice here. You put the carbon in the center. So that's our skeletal structure. All right, number 2 here on our Lewis diagrams. It says, count the total number of valence electrons. So let's do that. Hydrogen, has one valence electron, but there are 4 hydrogens. Carbon has 4 valence electrons. The total number of valence electrons in our molecule here is 8. And I'm going to draw those 8 valence electrons. Number 3 here in our rules says count the total number of electrons that you would have to have if each of the atoms had an inert gas configuration. All right? So these are the number that we've got, 8. And now we're calculating how many we would like to have in the optimal situation if each atom has an inert gas configuration. So let's do that. Well, hydrogen wants 2. And we have 4 hydrogens, so 4 times 2. Carbon wants 8. So if each of these atoms had an inert gas configuration, we'd need 16 electrons. All right? Step 4. Step 4 says to calculate the number of bonding electrons. The way you do that is by taking the total number of electrons that you would have to have if each atom had a noble gas configuration and subtract from it the total number of electrons that you actually do have. All right? So we're going to take 16, subtract from that 8. We're going to have 8 bonding electrons. The way I'm going to represent the 8 bonding electrons, or bonding electrons in general, is that I'm going to draw a red square around my electrons that are bonding electrons. So up here, these are the number of valence electrons I've got. It says 8 of those valence electrons are bonding electrons. So I'm going to draw a box. Those are my bonding electrons. Step 5 says to assign 2 bonding electrons to each bond. Well, let's do that. Assign 2 bonding electrons to each bond. Well, if we put 2 there, 2 there, 2 there, and 2 there, then we've used up all of our valence electrons and all of our bonding electrons in that structure. Number 6 says if you've got bonding electrons that remain, well, the answer is no. We used them all up. All right? And number 7 says, do we have any valence electrons left? The answer is no. We don't. We've used them all up. So we're done. And you can see that the hydrogen has an inert gas configuration around it. The carbon has an inert gas configuration, an octet of electrons around it. Hey, we're done with methane. But you could have done that anyway, right? Yes? Yeah, okay. All right. Here's another one. Oh, one other concept here. In this particular structure, carbon is a central atom. What I mean by a central atom is an atom to which everything else is bonded. All right? So sometimes we're going to ask you to write a Lewis structure, and we're going to tell you what atom is the central atom. So you know to put it in the center, and everything else gets connected to it. Okay, let's do another harder one. Here's this molecule. It's going to be hydrogen cyanide, HCN. First thing you have to do, according to our rule number 1, is to draw a skeletal structure. So you have the choice here of how to draw that skeletal structure. You can put the nitrogen in the center or the carbon in the center. Hydrogen's not going to go in the center because we know the hydrogen's terminal always. So what you often do as a first pass when you're drawing the skeletal structure is that you put the element with the lowest ionization energy in the middle. That's what our rule number 1 said. Element with lowest ionization energy goes in the middle. That often is true, but not always. This is a first pass. I'm going to show you a little bit later some cases where this won't be true and how we're going to determine that the lowest ionization element doesn't go in the center. All right? We're going to have a way to figure this out. But for right now, if you had no other choices, that's what you'd do. You'd write a structure with the lowest ionization energy element in the center. Okay, so we did that. Number 2, calculate the total number of valence electrons in this molecule. Well, hydrogen brings 1 valence electron into the party. Carbon brings 4. Nitrogen brings 5. We have a total of 10 valence electrons. I'm going to draw those 10 valence electrons. While you're learning to do this, you might also want to draw 10 valence electrons like this. Next step, calculate the total number of electrons each atom would have to have if, in an ideal world, they had a noble gas configuration, right, without sharing. Well, the total number of electrons that each atom, total number of electrons that we would have to have is 2 for the hydrogen, 8 for the carbon, and 8 for the nitrogen, a total number of 18. Step 4 says we calculate the number of bonding electrons. To do that, we subtract the total number that we would have to have for an inert gas configuration, 18, from the total number that we actually do have, which is 10. The result is 8 bonding electrons. I'm going to now draw this red square around the valence electrons that are going to be bonding electrons. All right, so here it goes. We got 8 bonding electrons. And 2 electrons left out here. We'll see that in a moment, where they go. Number 5, assign 2 bonding electrons to each bond. Okay, we'll put 2 there. We put 2 there. That's great. We've now used up 4 bonding electrons. But hey, we got 4 more bonding electrons left. So our next step is, do we have any bonding electrons left? We sure do. We got 4 of them. In that case, you start to make double bonds or triple bonds. All right? A double bond is one in which 4 electrons are shared. A triple bond is one in which 6 electrons are shared. In general, which atoms do you make double bonds or triple bonds between? Well, in general, double bonds form between carbon, nitrogen, oxygen, sulfur. Triple bonds usually restricted to carbon, nitrogen, and oxygen. All right? So in this case, we got a carbon and a nitrogen here. We got 4 extra bonding electrons. Well, what we're going to do is we're going to put these in between the carbon and the nitrogen. We're going to have a triple bond right there. All right? So we took care of all our bonding electrons now. Step 7, do we have any valence electrons remaining? Hey, we sure do. We've got 2 valence electrons remaining. What do we do with them? Well, we assign them as lone pairs. We look to see which atoms don't have an inert gas configuration. Well, hydrogen does. The carbon does now. It's got 8 electrons around it, but the nitrogen doesn't. It only has 6. So we're going to put those 2 extra valence electrons as a lone pair here on the nitrogen, and now the nitrogen has an octet around it. All right? These 2 electrons are called lone pairs. They don't participate in the chemical bonding. All right, so we did that one. Next one, thionyl chloride. So it's Cl2SO. How do you do this one? Well, as a first guess, the halogens usually are terminal atoms. So they're not bonded to anything else. All right, that's usually the case, not always, especially for chlorine. So we're going to put the chlorines out on the end somewhere. So then do we put oxygen in the center or sulfur in the center? Well, we're going to pick the lowest ionization element, energy element. We're going to put that in the center. That's going to be sulfur. So we'll try this as a skeletal structure. All right, so count the total number of valence electrons. Hey, chlorine brings 7 valence electrons into the party, and there are 2 chlorine atoms. Sulfur brings 6. Oxygen brings 6. Hey, we got a total number of 26 valence electrons. Let me draw them all out. Step number 3 is calculate the total number of electrons that we would have to have for each atom to have an inert gas configuration. Hey, we got 4 atoms here. Each one of them is going to want 8. We're going to have 32. Or that's what we would need for an inert gas configuration for each atom. Let's calculate the total number of bonding electrons. Well, that's 32 minus the number of valence electrons. That's 6. So of those 26 valence electrons, let me draw my box, my bonding box, around 6 of them. All right, next step is to assign those bonding electrons. Hey, that's going to be easy. Put 2 there, 2 there, and 2 there. That means we've just used up our 6 bonding electrons. Do we have any more left? No. There aren't going to be any double bonds here. However, we've got lots of valence electrons left, right? We've got 20 of them. We're going to have to make lone pairs with those 20 excess valence electrons. We're going to have to make 10 lone pairs so that each atom has an octet around it. So let's do that. We're going to put 6 of them around the oxygen. So now the oxygen has an octet. Another 6. There they go. Another 6 around the chlorine. There they go. Another 6 around this chlorine. There they go. And finally, we got 2 left. Well, that's going to have to go on the sulfur to make an octet. There it goes. Hey, we're done. We've used up all of our valence electrons, and we have an octet around each one of the atoms in that molecule. All right, so that's the basic procedure for writing these Lewis diagrams. But now, I talked about putting the lowest ionization energy element in the center sometimes. And I talked about, well, you got to try this structure first. Try this skeletal structure first. How do we really know if we've drawn the right Lewis diagram? Well, the way we're going to tell is by this concept. It's called formal charge. What formal charge is a measure of the extent to which an atom has gained or lost an electron when it has formed a chemical bond. All right? So compared to when it's an atom, the formal charge tells you how much of an electron that has been gained by it or lost by it. All right? I'll make that a little more real in just a moment. How do you assign a formal charge? Well, we got a recipe for this. That formal charge is the following. You count up the number of valence electrons on the free atom. We're going to call that V. You're going to subtract from it the number of electrons that are lone pairs on that atom in the molecule. So V minus L. And the third step is you're going to subtract 1/2 of the number of bonding electrons that atom has, or 1/2 the number of electrons that it shares in that molecule. So it's V minus L minus S over 2. S is the number of electrons it shares. That's the formal charge. Let's illustrate this. Let's take this ion, Cn minus. I already drew the Lewis structure here. So now what we're going to do is we're going to calculate the formal charge for carbon and the formal charge for nitrogen within this Lewis structure. Formal charges depend on the Lewis structure. All right, ready? Let's do it. For carbon, V is 4. We have 4 valence electrons. In this structure, L is 2. L is the number of lone pair electrons. Look at in this structure. Here are these electrons, the lone pair, that don't participate in the bond. We have 2 lone pair electrons. It's minus 2. And then we have to subtract from that minus 1/2 the number of shared electrons. Well, the number of shared electrons in the case of carbon is 6. We got a triple bond here. So that's 6 over 2. That's 3. Hey, the formal charge on carbon in this Lewis structure is -1. What we often do is we put a -1 somewhere near that carbon and circle it. That's the formal charge on the carbon. What that means is that the carbon has gained one more electron than it usually has as an atom. It's a little bit more negatively charged in this molecule than it is in the atom. Let's do nitrogen. Nitrogen, valence electrons is 5. Then minus the number of lone pairs, well, that's 2. Here's that lone pair. And then it's minus 1/2 the number of shared electrons or bonding electrons. Well, that's 3. The result is a formal charge of 0. And so what we would usually do is we'd write a 0 with a circle around it near that nitrogen. Okay? So the formal charge on carbon is -1. Formal charge on nitrogen is 0 in this structure. But now you got to check to make sure you did everything right. And here's the check. The check is that the total charges here, -1 plus 0, -1, the sum of the formal charges has to equal the overall charge on the molecule. Right? So -1 plus 0 is -1. Hey, that does equal the overall charge on the molecule. So we did everything right. Right? That's an important thing to check. All right, so that's how you calculate formal charge. Now, how do you use it? Well, first of all, before I tell you how you use it, let me just emphasize that formal charge is not oxidation number. Oxidation number does not depend on the Lewis structure. Formal charge depends on the Lewis structure. You're going to talk about oxidation number with Professor Drennan. If you don't know what it is, that's okay. You'll learn about it in a few weeks. But if you do know what it is, I just want to emphasize that formal charge is not the oxidation number. All right? Okay. So now, how do we use formal charge to make sure that we've got the correct Lewis structure? That's what you do. You use the formal charge. What you do is you realize that structures with lower absolute values of formal charge are the more stable structures. Structures which have formal charges on the atoms that are lower are more stable. Structures where the number of electrons that the atom has gained or lost in forming a molecule is smaller are the stable structures. This is really important because you're going to often have a situation where you've got 2 different skeletal structures. You've obeyed all of the rules for drawing the Lewis diagrams of those 2 different skeletal structures, those 2 different arrangements of atoms. But only one of those structures is going to be correct. And the one that's correct is going to have the lower set of absolute values of the formal charge. So let's illustrate this. Let's take this ion. It's the thiocyanate ion, NCS minus, as I have written it here. Now, if you were just told you've got an ion that has nitrogen, carbon, and sulfur in it, you might say, well, how do I start? Well, you could start by putting the element with the lowest ionization energy in the center. And that would be a good place to start. You should do that. But what we're going to do is we're going to look at all 3 possibilities here. We're going to look at a Lewis structure where the carbon's in the middle, where the sulfur is in the middle, and now where the nitrogen's in the middle. And we drew these Lewis structures. I've already drawn them here for you. according to our rules posted here on these walls. But only one of these structures is correct. And we're going to use the idea of formal charges to determine which one is correct, which one has the lowest energy. All right. So if we take this structure and we calculate the formal charge for nitrogen, we'll find it's -1. The formal charge on the carbon here is 0. The formal charge on the sulfur here is 0. All right, so I already did these calculations for you. If you sum up the formal charges, hey, we get -1. The overall charge on this ion is -1. Hey, we did that right. We did everything right. You should check your formal charges like this. Let's do the same thing for this structure. If we calculate the formal charge on carbon's -2. Formal charge on sulfur is 2. Formal charge on nitrogen's -1. Let's sum these up. When we do that, hey, we get a -1. It indeed matches the overall charge on the ion. Let's calculate the formal charges for each atom here. Sulfur is 0, nitrogen is 1, carbon's -2, overall charge -1. Hey, we did that right, okay? Now, which one of these structures is the lowest energy structure? Ready? I'm going to ask you to raise your hand or to scream. Is it structure number 1? Yes. Is it structure number 2? No. Is it structure number 3? No. You're right. It's structure number 1. Right? It has the lowest set of formal charges. -1, 0, 0. Only one atom here has a formal charge other than 0. These two structures have formal charges that are -2 or 2. Hey, I don't think that there is a structure on Earth, well, maybe there is, that has a formal charge of -2 or 2 that will make it the lowest energy structure. If you've got a structure with a -2 or 2, hey, that's very, very likely not the lowest energy structure. All right? So this is a powerful tool to know if you have drawn your skeleton correctly. Okay? Okay. So remember this. Really important. On an exam, we're going to tell you to draw the Lewis structure with the lowest energy. You're going to have to try several of them to see which one has the lowest set of absolute values for the formal charge. Question? I'm sorry? This one? Yes, this one. Okay. Number of valence electrons on the carbon is 4, minus the number of lone pairs on the carbon is 4. Right? That's 2, 4. Is that your question? Yeah, okay. Okay, other questions? Okay. Here's another use of the formal charge. This is also determining the skeletal structure here, but you'll see a problem in just a moment. Here's another special case. We have CH3NHO minus. How do you draw in this case here? How do you draw that skeletal structure? Can I have some lights on the board here? All right, CH3 okay, CH3 here, this is what we call a methyl group. It is always terminal, since the hydrogens are always terminal. So the structure looks like this, right? And the carbon then is bonded to the next element over. So if you see a structure like this, the first where you've got lots of different elements, the first pass, just take these elements in a row. The CH3, this methyl group, is bonded to the nitrogen. Okay. The next one is hydrogen, but we know we're not going to put the hydrogen between the nitrogen and the oxygen because the hydrogen's always terminal. So the hydrogen's either going to go here, or the hydrogen is going to go here. All right? And that's the question that we're going to ask here on this slide. Is this the correct structure, or is this the correct structure? So I drew the skeletal structures. I drew the Lewis diagrams. Which one's right? Okay. Well, if I go and calculate the formal charges here, I would find that the formal charge on oxygen is -1. And that the formal charge on all other atoms is 0. In this structure, if I go calculate the formal charge on the nitrogen in this structure is -1. And then the formal charge on all the other atoms are 0. Hey, we got a problem here. We got two different structures, and they have absolutely the same set of formal charges in terms of the absolute magnitudes, right? We have only one atom that has a -1 formal charge, only one atom that has one more electron than it usually does in its unbonded state, in its atomic state. So which one of these is correct? Well, it turns out that this structure is correct. It's correct because of this. It's correct because we put the formal charge on the most electronegative atom, which is oxygen. Oxygen's more electronegative than nitrogen. So that's the other key here, is that if you've got two structures, same sets of formal charges, and you have a choice of putting the minus formal charge on an atom, you put it on the most electronegative atom. That's going to be the lowest energy structure. In general here, we talked about the electronegativities. The electronegativity fluorine is greater than oxygen. It's greater than nitrogen. It's greater than carbon. All right? That is something that you'll need to know. Okay. So we've seen how this formal charge now is useful in figuring out whether or not we had the right skeletal structure to begin with. Okay? Now, here's another useful another utility of formal charge. Let's look at this structure, NO3 minus. Well, I know ahead of time that we're going to put this nitrogen in the center. If you just had NO3 minus and you didn't know anything, you would have to play around with some structures and look at formal charges. But I've already done that playing around, so I know to put nitrogen in the center. All right? Okay, but let's do the Lewis diagram for this. We count up the valence electrons. Hey, we've got 6 for every one of the oxygens, and 5 for the nitrogen. And now, hey, this one's important. We added an extra electron when we counted up the valence electrons. That extra valence electron comes because this is NO3 minus. We have an extra electron on NO3. So we have to count it in our valence electrons. If this was NO3 plus, hey, we would subtract 1 right here. But this is NO3 minus, so we got to add 1. All right? Okay, that's 24 valence electrons. Let me draw them all out. Number 3. Let's calculate the number of electrons that we would have to have if each atom had a noble gas configuration. That would be 32 because we got 4 atoms. Let's calculate the number of bonding electrons. Well, that's 32 minus 24, or 8. So of those 24 valence electrons, 8 of them are bonding electrons. Let's assign them. Well, here's 2, here's 2, there's 2. Hey, that's great. We used up 6. So do we have any remaining? We sure do. We got 2. So we're going to have to make one of these a double bond. All right? So we got one double bond there between nitrogen and oxygen. Now, we've got a lot of remaining valence electrons. All right, we've got 16 that are remaining. We're going to distribute them around the oxygens in order to make an octet around each atom. There we go, we did that. And so now we've used up all of our valence electrons. Let's calculate the formal charges. The formal charge on the singly bonded oxygen is -1. I put a -1 there, I'm going to put a -1 there. The formal charge on the doubly bonded oxygen right in here, hey, that's 0. I'm going to put a 0 there. The formal charge on the nitrogen, well, that's 1. I'm going to put a 1 there. If I sum up the formal charges, I get a -1. That does agree with the overall charge on this molecule, NO3-. So we did everything right. All right, but now you see something a little strange here, right? And that is, for whatever reason, I picked this nitrogen and oxygen to make a double bond. Hey, but I could have also made the double bond between this nitrogen and oxygen. And if I had calculated the formal charges, I would have identically the same set of formal charges. Or I could have picked this oxygen and nitrogen to put in the double bond. If I calculated the formal charges, I'd have the same set of formal charges. So we've got 3 different structures, all which have the same set of formal charges. What are we going to do here? Which one of these is correct? Well, when you've got this situation here, this is a hint that you've got what we call a resonance structure. All right? So if you have the same skeletal arrangement, and you've just got 3 different structures, and the electrons are in different places, and the same set of formal charges exist, this is a hint you have something called a resonance structure. What's a resonance structure? Well, here's the bottom line. In NO3-, if you look at the structure of that ion, you would not find that one of the nitrogen-oxygen bonds was a double bond and that the other 2 were single bonds. Right? A double bond is stronger than a single bond. A double bond is shorter than a single bond. So if you do the appropriate experiment, you can tell whether or not you have a shorter or a longer bond. You can tell whether you have a weaker or a stronger bond. The bottom line is that when you look at this molecule experimentally, you do not see one bond that's shorter and stronger than the other 2 nitrogen-oxygen bonds. What you find is that all 3 bonds are equivalent. All 3 bonds have the same strength and the same length. You find that the length of the nitrogen-oxygen bonds are a little bit shorter than those of a single bond, and you find that the nitrogen-oxygen bonds are uniformly, all 3 of them, a little bit stronger than a nitrogen-oxygen single bond. But not quite a double bond. What you find is that all of these 3 bonds is like a bond and a third. So what's happening here? What's happening here is that this extra pair of electrons, instead of being localized on just one of the nitrogen-oxygen bonds, those extra pair of electrons are actually delocalized over all 3 bonds. All right? And we call that a resonance hybrid. We denote that resonance hybrid in this way, with 3 different structures with double-headed arrows. right? This does not mean, this is important, this does not mean that the structure is flickering between here, here, and here. That's not what's happening. Rather, these two extra electrons are delocalized over all three bonds, such that the bond is like a bond and a third, rather than one bond or two bonds. This is called a resonance structure, a resonance hybrid, all right? And you'll be clued in that you've got this kind of resonance hybrid if you're able to write three structures with the same set of formal charges. You'll know to do this. Okay, have a nice, cool weekend. See you Wednesday.